The James Webb Space Telescope was not supposed to break physics. It was supposed to confirm it. That is not a cynical reading of the mission. That is what its designers said explicitly in the pre-launch documentation, in the scientific justification for its $10 billion price tag, in the decades of advocacy by the astronomers who championed it. Webb was built to see the first galaxies, the ones that formed in the universe's earliest chapters, too faint and too red-shifted for any previous instrument to detect. The expectation was that it would show us those first galaxies looking exactly the way the models predicted. Small, irregular, chaotic structures, still assembling themselves from the raw material of the early universe, primitive and faint. The models were built carefully. They were built over decades, tested against every observation from Hubble and Spitzer and Chandra, and every ground-based telescope with any claim to cosmological relevance. They were not guesses. They were the product of the best physics humanity has ever produced. General relativity, quantum field theory, computational cosmology, precision measurements of the cosmic microwave background, the lambda CDM model of cosmology, which predicts the structure and evolution of the universe from fractions of a second after the Big Bang to today, is one of the most successful scientific frameworks in the history of human thought. And then Webb looked at the early universe, and the early universe looked wrong. Not wrong in a minor, let us adjust a parameter way. Wrong in the way that means the models are missing something important. Wrong in a way that sent papers flooding into the Archive preprint server within months of the first data release. Wrong in a way that produced the kind of language that physicists do not use unless they mean it. Language like, in tension with our predictions, challenges the standard model. We do not understand what we are looking at. The astronomer, Garth Illingworth, who spent decades working on the science case for JWST, described the early results as seeing something in a different universe. Not his exact phrase in every telling, but the sentiment is precise. The galaxies Webb found in the earliest chapters of cosmic time do not look like the galaxies those models predicted. They are the wrong size, the wrong mass, the wrong maturity. They exist in numbers that the models say should be impossible. And they do it again and again, in survey after survey, in sample after sample, with a consistency that rules out the most convenient explanations. But impossible early galaxies are only the first disturbing thing. There are ancient spiral galaxies, the most structurally organized form a galaxy can take, that exist when the universe was barely 5% of its current age. There are black holes that have grown to masses of billions of solar masses in timescales that standard black hole physics says cannot produce them. There is a measurement of the universe's expansion rate that gives one answer when you look at the early universe, and a completely different answer when you look at the nearby universe. A discrepancy that has persisted for years, that JWST was supposed to resolve, and that JWST has instead confirmed. And there is, underneath all of this, the growing suspicion in the cosmological community that the standard model of cosmology, lambda CDM, the framework that has governed our understanding of the universe for 30 years, is not complete. That something is missing, something fundamental. This video is a journey through every major thing that James Webb has found that the universe was not supposed to show us. Not the beautiful things, not the nebulae and the stellar nurseries, as extraordinary as those are. The disturbing things, the things that do not fit, the things that are keeping theoretical cosmologists awake at night. We are going to travel through each one carefully and honestly, with the full weight of what the data is actually saying. We are going to look at what the models predicted, what Webb found instead, and what the gap between those two things means for our understanding of the universe we live in. It is a stranger universe than we thought. Let us go into it. Chapter 1: The telescope that was supposed to confirm everything. Before we can understand what Webb found that disturbed everyone, we need to understand what it was expected to find. And to understand that, we need to understand the standard story of how the universe makes galaxies. The universe began approximately 13.8 billion years ago in a state of extraordinary density and temperature, the Big Bang. In the first moments, it was a plasma of quarks and gluons, then of protons and neutrons, then of hydrogen and helium nuclei, then of neutral atoms when it cooled enough for electrons to bind to nuclei. At the moment of that binding, called recombination, occurring approximately 380,000 years after the Big Bang, the universe became transparent to radiation for the first time. The light released at that moment is still propagating through the universe today as the cosmic microwave background, the faint glow of radiation permeating space in every direction, carrying within its pattern of temperature fluctuations the imprinted memory of the universe's initial conditions. Those temperature fluctuations, tiny variations in density across the early universe at the level of 1 part in 100,000, are the seeds of everything that followed. Regions slightly denser than average had slightly more gravitational pull. They attracted more matter. They grew. Over hundreds of millions of years, gravity amplified the initial fluctuations, drawing matter into filaments and nodes, building the large-scale structure of the cosmic web. Within the densest nodes, dark matter halos formed first, invisible scaffolding around which ordinary gas could cool and collapse, forming the first stars and the first galaxies. This process, hierarchical structure formation, has a specific, well-defined sequence. Small structures form first because the density fluctuations that drive structure formation are largest on small scales. The first objects to form are the smallest, dense knots of gas collapsing to form the very first stars, and then collections of those stars assembling into the first proto-galaxies. These first galaxies are small and irregular, clumpy, asymmetric, actively star-forming, lacking the organized structures like spiral arms or smooth elliptical shapes that require billions of years of evolution to develop. Over cosmic time, these small structures merge with each other, building progressively larger and more organized systems. The large, structured galaxies we see nearby, spiral galaxies like the Milky Way, massive ellipticals containing trillions of stars, are the products of this long hierarchical assembly, and they are therefore late arrivals. They should not exist in the early universe. This was the prediction. Small, irregular, faint, early. Large, structured, massive, late. It was a good prediction. It was grounded in physics. It had been tested against the deepest observations Hubble could make. Hubble's ultra-deep field, the most sensitive image of the distant universe ever taken before Webb, showed distant galaxies that were indeed smaller and more irregular than nearby galaxies. The trend was in the right direction. The hierarchical story appeared to be working. And then Webb looked 800 million years further back in time and found things that are not small, not irregular, and not consistent with the hierarchical story. To understand how different Webb's instruments are from Hubble's, you need one specific number. Webb's primary mirror collects approximately 7 times more light than Hubble's. 7 times? That is not a minor improvement. In astronomy, light collecting area is everything. It determines how faint an object can be detected, how quickly a spectrum can be measured, how distant a galaxy can be confirmed. But Webb's advantage over Hubble is not primarily its mirror size. It is its wavelength range. The universe's expansion stretches the light from distant objects toward longer wavelengths, a phenomenon called cosmological redshift. A galaxy at the edge of Hubble's vision, at redshift Z equals 7, has its ultraviolet light stretched into the near-infrared. A galaxy at redshift Z equals 13, which Webb can reach but Hubble cannot, has its light stretched so far into the infrared that it is completely invisible to Hubble's detectors. Webb was designed from the ground up to see in the infrared. Its instruments are cooled to within a few degrees of absolute zero to prevent the telescope's own thermal emission from overwhelming the faint infrared signals it is trying to detect. Its orbit at Lagrange Point 2, 1.5 million kilometers from Earth, keeps it permanently shielded from the sun's heat. The result is an instrument that can peer further into the universe's past than any telescope before it, not by a small margin, but by an enormous one. Webb can detect galaxies from the first 300 million years of the universe's existence. The universe is 13.8 billion years old. Webb can see the universe when it was 2% of its current age. What it saw there is what this video is about. Chapter 2: The Impossible Galaxies. In the first months of Webb's scientific operations, something started showing up in the data that made astronomers uncomfortable. It was not a single galaxy. It was not an isolated curiosity that could be explained away as a rare statistical fluctuation. It was a population, a systematic excess of objects at high redshift, at the distances corresponding to the universe's first few 100 million years, that were too large, too massive, too bright, and too structurally mature to be consistent with. What the hierarchical structure formation model predicted should be there. The paper that crystallized the problem most dramatically was published in Nature in February 2023 by Ivo Labbé and colleagues. They identified 6 candidate galaxies at redshifts between Z equals 7 and Z equals 10, corresponding to the universe being between 500 and 700 million years old. Their estimated stellar masses, the total mass of stars contained within the galaxy, ranged from 10 billion to 100 billion solar masses. To understand why those numbers are alarming, you need a reference point. The Milky Way, our own galaxy, a large mature spiral galaxy that has been assembling itself for approximately 13 billion years, has a stellar mass of roughly 50 billion solar masses. It took our galaxy virtually all of cosmic time to accumulate that mass. The Labbé candidates had accumulated comparable masses in less than 700 million years, in less than 5% of the time our galaxy has had. The lambda CDM model makes specific predictions about the most massive galaxies that can exist at any given redshift. Those predictions are not arbitrary. They are derived from the known density of dark matter halos at different epochs and the physical processes of gas cooling and star formation. At redshift Z equals 7 to 10, the model says that the largest galaxies should have stellar masses of perhaps 1 to 10 billion solar masses, if you're being generous. Not 100 billion, not 50 billion. The Labe candidates at face value exceeded the maximum predicted mass at their epoch by factors of 10 or more. The paper was cautious, as it should be. The mass estimates were photometric, derived from the brightnesses and colors of the galaxies across different wavelength bands, not from direct spectroscopic measurements of their distances and compositions. Photometric redshifts and photometric mass estimates carry real uncertainties. A galaxy that appears to be at redshift Z equals 10 based on its colors could, in principle, be a lower redshift interloper, an unusual object whose spectral characteristics mimic those of a distant galaxy. The community called for spectroscopic follow-up. Webb provided it. The JADES program, JWST Advanced Deep Extragalactic Survey, delivered spectroscopic confirmation of multiple objects at extreme redshifts. The records fell in sequence: a confirmed galaxy at Z equals 10.6, then Z equals 11.5, then Z equals 12.5, then Z equals 13.2, and the current record holder as of 2024, JADES-GS-Z14-0, confirmed spectroscopically, at Z equals 14.32. This galaxy existed when the universe was approximately 290 million years old. At 290 million years, Lambda CDM predicts a universe still in the early stages of forming its first stars and proto-galactic clumps. Not a galaxy. Not a luminous, spatially extended, structured, chemically enriched system with a stellar mass of 500 million solar masses and a radius of 1,600 light-years. But the most alarming detail in the JADES GS Z14-0 data is not its mass or its size. It is a single spectral feature. The spectrum shows emission from oxygen. Oxygen is not produced in the Big Bang. The Big Bang produces hydrogen, helium, and trace amounts of lithium. Everything heavier, every element on the periodic table above lithium, is produced in stars through nuclear fusion in stellar cores and through the explosive nucleosynthesis of supernova. Oxygen requires stars to live and die, stars that are massive enough to produce oxygen in their cores and then explode in supernova, distributing that oxygen into the surrounding interstellar medium. For oxygen to be detectable in a galaxy at E equals 14.32, in a galaxy that existed when the universe was 290 million years old. That galaxy must have already completed at least one full cycle of star formation. Massive stars must have formed, lived their brief lives of a few million years, exploded in supernovae, and enriched the galaxy's gas with oxygen. All of this must have happened before 290 million years elapsed after the Big Bang. That means the first stars in that galaxy, the population 3 stars that initiated the first generation of star formation, must have ignited substantially before 290 million years, perhaps within the first 100 to 200 million years. That is almost incomprehensibly early by the Standard Model's timeline, and it means the entire sequence of early cosmic structure formation, the onset of star formation, the enrichment of early galaxies, the assembly of stellar mass, was compressed into a shorter timescale than any pre-JWST model predicted. The response from theorists has taken several forms, and it is worth examining each one honestly, because the quality of a scientific community's response to anomalous data tells you something important about the health of the science. The first response is model adjustment. Star formation in the early universe may have been more efficient than the models assumed. The feedback processes, supernovae explosions, radiation from massive stars, outflows from supermassive black holes, that in current models interrupt and regulate star formation, might have been less effective in the early universe. If early galaxies converted their gas to stars more efficiently, they would have grown more massive more quickly. This is physically plausible. The question is whether the degree of efficiency required to explain the JWST observations is itself physically plausible, or whether it requires star formation operating at rates that exceed what the available gas and the relevant physical timescales can support. Several analyses have found that even under maximally optimistic assumptions about star formation efficiency, the most massive JWST candidates at the highest redshifts remain difficult or impossible to explain within lambda CDM without some additional ingredient. The phrase maximally efficient in these analyses is not rhetorical. It means convert every available atom of gas into stars as fast as physics allows, with no interruptions from feedback, from day one. Even that extreme scenario strains to produce what Webb is finding. The second response is observational uncertainty. Photometric mass estimates have systematic uncertainties of a factor of 3 or more. Some of the photometric candidates may be overestimated in mass. Dust attenuation, the absorption of some fraction of stellar light by dust within the galaxy, can make galaxies appear less luminous than they are, which means the inferred stellar populations may be systematically in error. These are legitimate scientific questions. But for every photometric candidate that might be resolved by these uncertainties, there are spectroscopically confirmed objects whose redshifts are beyond doubt. JADES-GS-Z14-0 is not a photometric candidate. It is a spectroscopically confirmed galaxy with a spectroscopically confirmed oxygen detection. Its existence at Z equals 14.32 is not uncertain. The third response is the one that carries the most weight in the long run. Perhaps lambda CDM needs modification at a more fundamental level. Not just in the galaxy formation, physics built on top of the cosmological framework, but in the cosmological framework itself. Perhaps the initial conditions set by inflation produced more power on small scales than the standard inflationary models predict, seeding the denser than expected dark matter halos that would allow early galaxies to assemble more quickly. Perhaps the dark matter behaves differently than the cold, collisionless particles of the standard model. Perhaps early dark matter interactions changed the halo mass function in ways that accelerated structure formation. Perhaps there is new physics in the early universe, operating at energies and epochs not yet probed by any other observation, that the standard model simply does not contain. None of these possibilities has achieved consensus. All of them are being actively investigated. The impossibly early galaxies are real. They are in the data, and they do not fit. Chapter 3, The Ancient Spirals That Should Not Exist. The impossible mass of early galaxies is one category of disturbing finding, but Webb has added a second related category that in some ways is even more visually and intuitively striking: the appearance of structure. A spiral galaxy is one of the most beautiful objects in the universe and one of the most structurally complex. The elegant arms curving outward from a central bulge, traced by young blue stars and glowing gas clouds, are not a simple consequence of gravity alone. They are the product of a specific dynamical process: density waves propagating through a rotating disk that requires the galaxy to have already developed a stable, organized disk structure. Forming a spiral galaxy requires billions of years of evolution. First, the initial assembly of the disk, then the development of differential rotation, then the establishment of the density wave pattern that produces the spiral morphology. In the standard model, spiral galaxies are late-type objects. They are the products of settled, mature galactic systems. You would not expect to find a well-developed spiral galaxy in the early universe, any more than you would expect to find a fully grown oak tree in the first few months of a forest's existence. In 2023, a team led by Luca Constantin published results in Nature Astronomy describing the discovery of a remarkably well-developed spiral galaxy at redshift Z equals 4.41, a time when the universe was approximately 1.4 billion years old. The galaxy, designated Sears-2112, was found in the Sears survey data. Its spiral structure was not a marginal detection. It was clearly resolved in the Webb imagery, showing two well-defined spiral arms with the characteristic morphology of nearby spiral galaxies. At 1.4 billion years after the Big Bang, the universe had existed for approximately 10% of its current age. Lambda CDM models predict that stable spiral disk galaxies should not yet exist in significant numbers at this epoch. The dynamics required to produce the spiral structure, the gravitational stability of the disk, the differential rotation, the density wave amplification, require a level of dynamical maturity that takes considerably longer to develop than 1.4 billion years. Particularly in the turbulent, high gas fraction, rapidly star-forming environment of the early universe. Sears-2112 was not the only case. Subsequent Webb surveys identified additional high redshift galaxies showing unexpectedly regular disk structures, and, in some cases, spiral morphology at redshifts that challenge the predicted timeline of morphological evolution. The systematic finding is that the early universe contains a higher fraction of morphologically regular, disk-dominated galaxies than Lambda CDM simulations predict. The early universe is more settled, more organized, more structurally mature than it should be. The theoretical challenge posed by early disk galaxies is subtly different from the challenge posed by early massive galaxies, though they are related. The problem with massive early galaxies is primarily one of assembly time. How do you build so much stellar mass so quickly? The problem with early disk galaxies is primarily one of dynamical time. How do you establish a stable, regular disk structure in an environment that is supposed to be too turbulent, too merger-prone, too gas-rich, and dynamically hot to permit the ordered rotation that disk galaxies require. One proposed answer involves the role of dark matter halos in providing a gravitational potential that stabilizes the disk against the disruptive effects of mergers and feedback. If the dark matter halos of early galaxies were particularly well suited to hosting stable disks, perhaps because their formation history differed from standard predictions in ways that reduced the frequency of destabilizing merger events, then early disk morphology might be more common than the simulations suggest. Another proposed answer involves the initial conditions of disk formation. If early galaxies accreted their gas in more organized, filamentary streams, cold flows of gas along the cosmic web's filaments, flowing directly into the galaxy's nascent disk, rather than through the chaotic mergers that dominate in some models of early galaxy formation, the disk could establish its structure more quickly and more stably. This cold accretion scenario is consistent with some cosmological simulations, but not with others. And the observational constraints from Webb are providing new leverage on which scenario is more accurate. Neither explanation is fully satisfying. Neither completely resolves the tension between the observed frequency of early disk galaxies and the standard model's predictions. What they do is confirm that the early universe was organizing itself more rapidly and more efficiently than the models were built to accommodate. The early spirals and the impossibly massive galaxies tell the same story in different languages. The universe's first billion years was not the primitive, chaotic, slowly assembling epoch that the standard model predicted. It was dynamic, efficient, and structurally sophisticated in ways that our best models consistently underestimated. Chapter 4: The Black Holes That Grew Too Fast. If the galaxies of the early universe are disturbing, their central black holes are more disturbing still. Virtually every large galaxy in the present-day universe contains a supermassive black hole at its center. A black hole with a mass ranging from millions to billions of solar masses, residing at the gravitational heart of the galaxy. The Milky Way's central black hole, Sagittarius A star, has a mass of approximately 4 million solar masses. The black hole at the center of the galaxy, M87, the one famously imaged by the Event Horizon Telescope in 2019, has a mass of approximately 6.5 billion solar masses. How did these objects grow so large? In the standard model, supermassive black holes grow primarily through accretion, the infall of gas and dust onto the black hole, which releases enormous amounts of energy as the infalling material is compressed and heated, producing the brilliant sources of radiation called quasars, or active galactic nuclei, when a supermassive black hole is actively accreting at high rates. Black holes also grow through mergers, the collision and coalescence of two black holes when their host galaxies merge. There is a physical limit on how fast a black hole can accrete. As the infalling material heats up, it produces radiation that pushes outward, radiation pressure that opposes further infall. When the radiation pressure exactly balances the gravitational pull, the Eddington limit, the accretion process is in equilibrium. Accretion at the Eddington rate is the maximum sustained accretion rate a black hole can maintain over long timescales under normal conditions. It sets a specific timescale, the Salpeter time, approximately 45 million years, for the black hole to double its mass at maximum Eddington rate accretion. Working backwards from the salpeter time, there is a maximum mass that a black hole can reach in any given amount of time, starting from any given initial seed mass. Start with a stellar mass black hole of 10 solar masses at the Big Bang. Accrete continuously at the Eddington rate for 800 million years to redshift z equals 7. And you can produce a black hole of approximately 10 million to 1 billion solar masses, depending on the exact parameters. That sounds like a lot. 1 billion solar masses. Webb is finding quasars, actively accreting supermassive black holes, at redshift z equals 7 and beyond, with black hole masses of 1 billion, 5 billion, 10 billion solar masses, at a cosmic age of 700 to 800 million years. Some of these objects, given realistic seed masses and the Eddington accretion limit, would have required a head start that is physically impossible in the standard model. They would have needed to begin growing from seeds more massive than any known stellar mass black hole formation mechanism can produce, accreting at the maximum possible rate continuously, without interruption, from the very first moment of their existence. The quasar J0313-1806, identified before Webb, but at redshift z equals 7.64, contains a black hole of 1.6 billion solar masses when the universe was approximately 670 million years old. To reach that mass by that age, starting from a conventional stellar mass seed, would require continuous Eddington rate accretion for the entire preceding lifetime of the universe. There was no preceding lifetime of the universe at that point. 670 million years is all the time that had elapsed. The math, at face value, does not work. Webb has deepened this problem by enabling more detailed observations of high redshift quasars and by identifying a new population of objects that the pre-Webb surveys could not detect. The JWST, JADES, and CEERS surveys have identified compact, luminous, high redshift sources, nicknamed little red dots by the astronomers who first catalogued them, that appear to be low luminosity AGN, active galactic nuclei, at very high redshifts. Some of these objects contain black holes with masses that appear overmassive relative to their host galaxies, larger compared to the stellar mass of the surrounding galaxy than the relationship between black hole mass and galaxy mass observed in the local universe. In the nearby universe, there is a tight relationship between the mass of a galaxy's central black hole and various properties of the galaxy: the velocity dispersion of the galaxy's bulge stars, the total stellar mass of the bulge. This M-sigma relation implies that black holes and galaxies co-evolved, that their growth was somehow coupled, regulated by feedback processes that prevented either from getting too far ahead of the other. In the early universe, according to JWST data, the black holes appear to have gotten ahead. They are overmassive for their host galaxies. They grew faster than the galaxies around them. The proposed explanations fall into two categories. The first involves exotic black hole seed mechanisms, direct collapse black holes, formed not from the death of ordinary massive stars, but from the catastrophic collapse of enormous clouds of gas. Clouds massive enough that the gas cloud itself, rather than fragmenting into stars, collapsed directly into a black hole of perhaps 100,000 to 1 million solar masses. Such direct collapse black holes, if they exist, would provide a much more massive starting point for supermassive black hole growth, making the observed masses at high redshift more achievable within standard accretion physics. Direct collapse black holes have been theorized for years. They have not been directly confirmed observationally. Webb is providing new upper limits on their abundance at high redshift. The second category involves super-Eddington accretion rates that exceed the standard Eddington limit. The Eddington limit is not an absolute physical barrier in the way that the speed of light is. In certain geometries of the accretion flow, in certain radiation transfer regimes, accretion at rates several times the Eddington rate is theoretically possible for limited periods. If early black holes underwent episodes of super-Eddington accretion, their growth could have been accelerated beyond what the standard salpeter time calculation permits. Again, this is a physically plausible proposal. Again, it has not been directly confirmed. And even super-Eddington accretion, at realistic rates and realistic duty cycles, struggles to fully account for the most extreme high redshift masses that Webb is finding. The black hole problem is, in a sense, the sharpest version of a pattern that runs through all of Webb's disturbing findings. The early universe is not just slightly ahead of schedule. It is consistently, systematically, and significantly ahead of schedule in its galaxy masses, in its morphological development, in its chemical enrichment, and in its black hole growth. The magnitude of the discrepancy with the standard model varies from finding to finding, but the direction is the same in every case. The early universe was more developed, faster, than our best models said it could be. That consistency of direction is not what you expect from random measurement errors or statistical fluctuations. Random errors scatter in both directions. Systematic observational biases can in principle push in one direction, and the field takes those possibilities seriously. But the convergence of multiple independent lines of evidence, different surveys, different teams, different observational techniques, different physical phenomena, all pointing towards the same conclusion, is difficult to attribute to instrumental or observational artifacts. It looks increasingly like a physical signal, a signal that the standard model is missing something about the early universe. Chapter 5: A measurement that gives two different answers. If the galaxy and black hole problems represent one class of challenge to the standard model, the things formed too early problem, then the Hubble tension represents a different class entirely. Not a problem about what formed when, but a problem about the most fundamental parameter of cosmological dynamics: the rate at which the universe is expanding. The Hubble constant, denoted h0, pronounced h0, is the number that describes the current rate of cosmic expansion. It tells you how fast a galaxy is moving away from us per unit of distance. It was first measured by Edwin Hubble in 1929 using Cepheid variable stars in nearby galaxies, and the discovery of cosmic expansion was the foundation on which the entire modern cosmological edifice was built. Every estimate of the age of the universe, every extrapolation back to the Big Bang, every model of cosmic structure formation depends on knowing h0 accurately. Measuring h0 accurately has been one of the central projects of observational cosmology for nearly a century. And in the past decade, something troubling has happened. Two independent, precise, well-validated methods of measuring H0 have converged on values that disagree with each other. The first method is the late universe measurement, the cosmic distance ladder. The principle is straightforward. Measure the distance to a nearby galaxy using parallax or Cepheid variables. Use that calibration to measure the distance to more distant galaxies using Type 1a supernovae, and derive H0 from the relationship between distance and recession velocity across cosmological scales. The distance ladder has been extended, refined, and checked against itself for decades. The SH0ES team, supernova H0 for the equation of state of dark energy, has been the primary driver of precision in this method, using Hubble Space Telescope Cepheid observations in dozens of galaxies as the base of the ladder. The SH0ES team's most recent value, H0 equals 73 kilometers per second per megaparsec. A galaxy 1 megaparsec, about 3.26 million light-years, away is receding at 73 kilometers per second. The second method is the early universe measurement, the cosmic microwave background. The CMB, mapped with extraordinary precision by the Planck satellite, encodes in its temperature fluctuation pattern a detailed record of the physical conditions of the early universe. Within the lambda CDM framework, the parameters of the model, including H0, can be inferred from a fit to the CMB data. The Planck collaboration's value, H0 equals 67.4 kilometers per second per megaparsec. 73 versus 67.4, a difference of approximately 8%. In a field where measurements are precise to 1%, this is enormous. The statistical significance of the discrepancy is approximately 5 sigma, the threshold at which, in particle physics, a result is considered a discovery. In cosmology, a 5 sigma discrepancy between two precision measurements of the same fundamental constant is not just a disagreement, it is a crisis. The natural first response was to look for systematic errors. Surely one of the measurements was wrong. The distance ladder depends on calibrations that cascade from rung to rung. Errors at the base of the ladder propagate to the top. Maybe the Cepheid calibrations were contaminated by crowding effects, multiple stars blending into what appeared to be a single Cepheid. Maybe the metallicity corrections for Cepheid pulsation periods were systematically off. Maybe the Type 1a supernova sample was contaminated by unusual events that did not represent the standard candle behavior. These were all plausible hypotheses, and the field pursued them rigorously. This is where Webb enters the story with decisive consequences. Webb's infrared sensitivity and angular resolution are specifically advantageous for Cepheid observations. At infrared wavelengths, dust extinction, the absorption of light by interstellar dust that complicates optical measurements, is reduced. Webb's higher angular resolution, compared to Hubble, allows it to distinguish individual Cepheids from nearby stellar companions that could blend with the Cepheid in Hubble's less resolved images. In 2023, the SH0ES team used Webb observations of Cepheids in the galaxy NGC4258, the most important calibration galaxy for the distance ladder, to directly test whether the crowding and blending effects that were hypothesized to produce the high H0 value were real. They were not. Webb's measurements confirmed the Cepheid distances. The crowding corrections applied in the Hubble-based analysis were accurate. The distance ladder result at h0 equals 73 was not inflated by the proposed systematic errors. Webb's data sharpened the distance measurement, reduced the uncertainty, and arrived at the same answer as before. The Hubble tension did not go away. It became more certain. There is a specific, important way to understand what a persisting 5 sigma tension means after systematic errors have been ruled out. It means one of the following things must be true. Either there remain systematic errors in one or both measurements that are subtle enough to have escaped all scrutiny so far, a possibility that can never be entirely ruled out, but that becomes less probable with every additional precision measurement. Or the universe does not behave the same way in its early history as it does today, in a way that the standard lambda CDM model does not account for. That second option is the cosmologically radical one, and it is the one that a growing fraction of the theoretical community believes is correct. Lambda CDM assumes that dark energy is a cosmological constant, a fixed, unchanging energy density of empty space that drives the accelerating expansion of the universe. If dark energy is not constant, if it had a different value in the early universe than it does today, if it evolved or decayed over cosmic time, then the early universe and late universe measurements would be extracting H0 under different dark energy conditions, and they would be expected to give different answers. There is also a class of models involving early dark energy, an additional component of dark energy that was significant in the early universe, before the last scattering surface that the CMB samples, and has since diluted away as the universe expanded. Early dark energy models can, in principle, reconcile the CMB inferred H0 with the distance ladder H0 by modifying the sound horizon, the characteristic scale imprinted in the CMB by acoustic oscillations of the early plasma, in ways that shift the CMB's inferred H0 upward. Early dark energy is not a trivial modification. It requires new physics, a new scalar field, or a new component of the universe's energy budget with specific properties. But it is physical, it is testable, and it is being actively developed and constrained against observations. The alternatives are also active areas of research: modified gravity theories, interacting dark matter-dark energy models, new relativistic species that contributed to the energy density of the early universe and changed the rate of expansion before recombination. Each of these proposals touches the H0 discrepancy in a different way. Each one makes predictions that can be tested against the growing body of cosmological data, including the JWST data on galaxy clustering, early galaxy abundances, and the expansion history inferred from high redshift objects. What is not happening is resolution. The Hubble tension has been known for years, and it has not resolved. If anything, it has hardened. The increasing precision of measurements on both sides of the tension, the distance ladder, and the CMB, have not moved the two values toward each other. They have moved the uncertainties downward while keeping the central values apart. The tension is becoming more definite, not less. And Webb's confirmation of the SH0ES result has closed off the most obvious escape route. The universe, when you ask it how fast it is expanding, gives you two different answers. One from the early universe, one from the late universe. And they do not agree. That should not be possible if our model of the universe is complete. The fact that it is happening is telling us something. We do not yet know what. But the silence is getting louder. It is worth pausing here to appreciate the specific strangeness of this situation. The Hubble constant is not some arcane technical parameter relevant only to specialists. It too is the universe's fundamental clock, the number that converts observed recession velocities into cosmic distances, that anchors every distance measurement in observational cosmology, that sets the age of the universe, that determines how far light has had time to travel since the Big Bang. If two independent precision methods of measuring this number disagree at 5 sigma, it does not merely mean that one measurement is slightly wrong. It means that either our measurement infrastructure has hidden systematic errors that have survived years of scrutiny, or the cosmological model we use to interpret at least one of the measurements is missing a physical ingredient that affects the answer. The second possibility has increasingly specific implications. The CMB measurement of H0 is not a direct measurement. It is an inference from the CMB data using the lambda CDM model. If something about the physics of the early universe differs from what lambda CDM assumes, if the early universe contained an extra energy component, or if dark energy behaved differently at early times, or if the dark matter properties deviated from cold and collisionless, then the CMB would point to a different H0 than the distance ladder measures directly in the late universe. The tension is not just a number problem, it is a physics problem. And Webb has, by ruling out the distance ladder systematic errors, made it unambiguously, irreducibly a physics problem. The cosmological community has been forced to choose between two uncomfortable positions. Either the universe is more complex than the best model says, or the measurements are wrong in ways no one can find. The measurements are holding up under every test, which means the universe is more complex. Chapter 6: Dark Energy's Strange Behavior. Underneath the Hubble tension, there is a deeper question, one that the JWST data is beginning to probe in ways no previous telescope could, and that may ultimately require a more fundamental revision of cosmology than any of the individual anomalies we have discussed so far. That question is, what is dark energy? The question sounds almost rhetorical. We do not know what dark energy is. That is not a recent embarrassment. We have known since 1998, when two independent teams of supernova observers discovered that the universe's expansion was accelerating rather than decelerating, that something was causing cosmic expansion to speed up, something that acted like a repulsive force distributed uniformly throughout all of space, something with negative pressure in the thermodynamic sense that counteracted gravity on the largest scales. That something was named dark energy. The simplest mathematical description of dark energy is the cosmological constant, the lambda in lambda CDM, a constant term in Einstein's field equations representing a fixed energy density of empty space. Quantum field theory predicts that empty space should indeed have a vacuum, energy from quantum fluctuations. The problem is that the quantum field theory prediction for the vacuum energy is approximately 120 orders of magnitude larger than the observed cosmological constant. 120 orders of magnitude, a factor of 10 to the power of 120, a 1 followed by 120 zeros. This is Without any competition, the largest discrepancy between theoretical prediction and observation in the history of physics. It is called the cosmological constant problem, and despite decades of effort, no one has explained it. The standard resolution to the cosmological constant problem is not a solution. It is an acceptance. Physicists accept that some unknown mechanism cancels the enormous quantum vacuum energy down to the tiny observed value, and that the cosmological constant simply has the value it has. This is not satisfying theoretically, but empirically, the cosmological constant model fits the data exceptionally well. The CMB, the baryon acoustic oscillations, the supernova distance measurements, all of them are consistent with dark energy as a cosmological constant with equation of state parameter W equals -1. But the Hubble tension is one of several hints that dark energy may not be constant, that the equation of state parameter may not be -1, that W may vary with time, a scenario called dynamical dark energy or quintessence, in which dark energy is not a fixed property of empty space, but an evolving field with its own dynamics. This is where the DESI, Dark Energy Spectroscopic Instrument, results published in 2024 became significant. DSI measured baryon acoustic oscillations across the cosmic history, using a survey of approximately 6 million galaxies and quasars. The baryon acoustic oscillation scale, a characteristic clustering length imprinted in the distribution of galaxies by the acoustic oscillations of the early universe, acts as a standard ruler across cosmic time, allowing precise measurements of the expansion, history at different epochs. DSI's first-year results showed a hint, at approximately the 2 to 3 sigma level, that dark energy's equation of state parameter had evolved over time. The best fit model had W changing from a value less than -1 in the early universe to a value greater than -1 today. This is a pattern called phantom crossing, and it is not predicted by simple quintessence models. It would require more exotic dark energy physics, a dark energy model with specific internal dynamics that produce the crossing behavior. Is this a real signal or a statistical fluctuation? The DC collaboration was explicit. More data is needed. Their full 5-year survey will include 40 million galaxies compared to the 6 million in the first year data. By the end of the survey, the statistical question should be decisively resolved. But the DESI hint, combined with the Hubble tension, and combined with the theoretical dissatisfaction with the cosmological constant problem, is producing a growing sense within the cosmological community that the lambda in lambda CDM may be the wrong model for dark energy. Webb's role in this investigation is specific and important. Webb can observe Type 1a supernova at higher redshifts than Hubble could, extending the supernova distance measurements to earlier epochs, where the dark energy equation of state has more leverage on the expansion history. It can observe galaxy clustering at high redshift, providing independent baryon acoustic oscillation measurements at Z greater than 2 that complement DESI's lower redshift results. And the Hubble tension, which may itself be a signal of evolving dark energy, has been sharpened by Webb in ways that increase the pressure on models that assume a constant cosmological constant. What dark energy actually is remains completely unknown. But for the first time in decades, The observational evidence is beginning to suggest that the simplest answer, a cosmological constant, may not be the right one. If dark energy is dynamic, if it evolves, if it changes over cosmic time, then the entire expansion history of the universe is different from what lambda CDM predicts. The history of structure formation is different. The ultimate fate of the universe, whether it will expand forever, recollapse, or tear itself apart in a big rip, is different. That is not a small revision. That is a change to the most fundamental level of our cosmological description. And Webb, by providing precision measurements of the universe's expansion history at epochs no previous instrument could reach, is one of the primary tools by which the question will ultimately be answered. Chapter 7: The First Light, and what it reveals about our origins. There is a period in the universe's history so remote and so poorly understood that cosmologists gave it a name that sounds more like myth than physics. They call it the Cosmic Dawn. It refers to the epoch when the first stars ignited, when the universe transitioned from its long, dark silence after recombination into a luminous, star-filled cosmos. It is the moment the lights turned on, and because those first stars were the factories that produced every heavy element in the periodic table, because they were the sources that reionized the neutral hydrogen fog filling the universe, because their explosions seeded the interstellar medium with the raw material from which all subsequent generations of stars and planets and, ultimately, life would be built. The cosmic dawn is not just a cosmological event. It is the origin point of chemistry, the origin point of complexity. In a very real sense, the origin point of everything that makes the universe interesting. Before Webb, we could not see it. We could infer it. We could model it. We could see its echoes in the cosmic microwave background and in the chemical compositions of the oldest stars we could observe. But the actual moment, the actual epoch of the first stars, and the first light was invisible to every instrument we had built, too redshifted, too faint, too far back in time. Webb was designed specifically to reach it, and what it is finding there is consistent with every other disturbing thing this video has cataloged, not quite what the models predicted. The first stars, called Population 3 stars, are theorized to have been profoundly different from any star alive today. They formed from gas that was chemically pristine, pure hydrogen and helium, the primordial outputs of Big Bang nucleosynthesis, with essentially no heavy elements at all. The absence of heavy elements is not merely a chemical detail. It changes the physics of star formation fundamentally. Heavy elements, carbon, oxygen, silicon, iron, radiate energy efficiently through their spectral lines, allowing gas clouds to cool as they collapse, fragmenting into clumps that form stars of modest mass. Without heavy elements, the cooling is far less efficient. Gas, clouds cool and collapse more slowly, and the resulting stars tend to be far more massive, hundreds to potentially thousands of solar masses. A population 3 star of several hundred solar masses is a physically extreme object. Its core temperature is hundreds of millions of degrees. Its luminosity is millions of times the sun's. Its surface radiates at temperatures hot enough to ionize not just hydrogen, but helium, producing photons energetic enough to carve ionized bubbles in the neutral hydrogen fog around the galaxy, beginning the process of cosmic reionization. Its lifespan is measured not in billions of years, but in millions, perhaps 2 to 3 million years for the most massive. It is, by every measure, a brief and violent contributor to the universe's early history. And when it dies, in a supernova or a hypernova, or, for the very most massive, by direct collapse into a black hole, it disperses the heavy elements it has forged in its core into the surrounding interstellar medium, enriching the gas that will form the next generation of stars. Population 3 stars are, in the origin story of chemistry, the first act. Everything on the periodic table above lithium traces its ancestry to these objects. The oxygen you are breathing right now was forged in the core of a star that lived and died before the sun was born. The carbon that is the backbone of every molecule in your body has been through stellar interiors, probably multiple times, in multiple stars, across multiple generations, before it ended up in you. The iron in your blood was forged in a supernova. These are not poetic metaphors. They are nuclear astrophysics. And the chain begins with the population 3 stars that Webb is now, for the first time, approaching observationally. The most direct evidence for population 3 stars would be the detection of their specific spectral signatures, particularly the Lyman alpha line of hydrogen and, crucially, helium emission lines that require the extremely high radiation temperatures only population 3 stars produce. In 2023, a team led by Callum Whitten reported the detection in JWST spectroscopic data of multiple unusually intense helium emission features in a galaxy at redshift c equals 6.6. The specific helium line detected, HE21640, requires photons energetic enough to strip an electron from singly ionized helium. Producing those photons requires stellar surface temperatures above 50,000 to 80,000 Kelvin. The hottest ordinary metal-poor stars reach perhaps 50,000 Kelvin. Population 3 stars, modeled at several hundred solar masses, would reach 100,000 Kelvin or higher. The Whitten team was careful, appropriately careful. They noted that the helium emission was consistent with population 3 stars, but could also be explained by other extreme objects. Very massive stars with unusual compositions, or compact X-ray sources. They did not claim a confirmed population 3 detection. They presented the observation as a candidate that warranted further investigation. This is how science at the frontier is supposed to work. You find a signal that is consistent with the thing you have been looking for. You document it precisely. You acknowledge alternative explanations, and you call for follow-up observations to discriminate between them. The follow-up is ongoing, and the broader context that the helium detection fits into, the consistent picture of an early universe that was forming stars more efficiently, enriching its gas more rapidly, and producing massive objects more readily than the models predicted, makes the population 3 hypothesis more plausible, not less, as a contributor to the anomalous observations Webb is making. It is worth pausing here to appreciate what it would mean to actually confirm the existence of population 3 stars observationally. These are objects that have been theorized for decades but never seen. Every model of early galaxy formation, every simulation of cosmic chemical enrichment, every theory of how the first supermassive black holes grew, has population 3 stars as a foundational ingredient whose properties are inferred rather than observed. The mass distribution of population 3 stars, how massive they typically were, whether they tended to form in clusters or in isolation, what fraction of them died as supernovae versus collapsing directly into black holes, determines almost everything about the subsequent chemical and structural evolution of the early universe. If population 3 stars were typically very massive, hundreds of solar masses, they would have been extraordinarily luminous but extremely short-lived, and their deaths would have distributed enormous quantities of heavy elements into the surrounding interstellar medium very rapidly, jump-starting the chemical enrichment that made subsequent generations of stars and eventually planets possible. They would also have been the seeds of some of the most massive black holes in the early universe. Conversely, if population 3 stars were typically less massive, tens of solar masses rather than hundreds, their enrichment of the interstellar medium would have been slower and less concentrated, and the chemical evolution of the early universe would have proceeded at a more measured pace. The difference between these scenarios matters enormously for the impossible early galaxy problem. More massive population 3 stars mean faster chemical enrichment, which means gas in early galaxies could cool more efficiently, which means star formation could proceed faster, which means early galaxies could assemble more stellar mass more quickly. A population 3 mass function skewed toward very massive stars is not just theoretically interesting. It is one of the physical mechanisms that might reconcile the JWST early galaxy data with the rest of the standard model. Webb's observations of population 3 candidates are therefore not merely historically interesting documentation of the first generation of cosmic objects. They are constraints on one of the key physical ingredients that determines whether the impossible early galaxies can be explained within a modified standard framework or require entirely new cosmological physics. There is a related JWST finding that cuts even more directly to the question of when and how the universe first lit up, and it concerns the topology of cosmic reionization. Reionization, the process by which the neutral hydrogen fog of the early universe was ionized by ultraviolet photons from the first stars and galaxies, did not happen uniformly. It was patchy. Ionized bubbles grew around the first luminous sources, expanding as the sources grew brighter and more numerous, eventually merging into a fully ionized intergalactic medium. The geometry and timing of this patchy process encodes information about the earliest cosmic structures. Webb's deep spectroscopic surveys are beginning to map this topology in unprecedented detail. By observing the spectra of high redshift galaxies and quasars and measuring the absorption of their light by the neutral hydrogen along the line of sight, a technique called Gunn-Peterson absorption, Webb can determine which regions of space were ionized and which were not at different epochs, effectively mapping the progress of reionization across cosmic time and space. The early results suggest that reionization may have been more complete, more advanced at earlier times than some models predicted, consistent with the broader pattern of an early universe that was more active than expected. This has a specific implication that goes beyond cosmological modeling. If reionization was driven by the first galaxies, and if those galaxies were more numerous and more luminous at earlier times than the models predicted, as the impossible early galaxy findings suggest, then the reionization timeline was also shifted earlier. The Sao universe became transparent to ultraviolet light sooner. The light from the first stars reached farther sooner. The entire temporal sequence of early cosmic history is compressed toward earlier times compared to the Standard Model's predictions. Every piece of evidence Webb is gathering from the cosmic dawn is pointing in the same direction. The universe was ahead of schedule. Consistently, systematically, in every physical process that can be probed at these epochs. And that systematic ahead of schedule quality is the signature of something the Standard Model is not capturing. Not a random error, not a localized anomaly, a coherent directional discrepancy between prediction and observation, running across multiple independent phenomena that is becoming harder to dismiss and more demanding of explanation with every new data release. Chapter 8. The Cosmic Web at its breaking point. The individual anomalies we have cataloged, the early massive galaxies, the ancient spirals, the overgrown black holes, the Hubble tension, the dark energy hints, are each individually significant. But there is a category of JWST finding that puts all of them into a wider context, and that may represent the most fundamental challenge to the Standard Model of all. It concerns the largest structures in the universe. The cosmic web, the vast network of filaments, nodes, and voids that constitutes the large-scale architecture of matter distribution across the universe, is Lambda CDM's greatest triumph. The model predicted the web before it was observed. The first large-scale galaxy surveys in the 1980s and 1990s confirmed the filamentary structure that the simulations had forecast. The galaxy clusters, the superclusters, the voids, hundreds of millions of light-years across. The great walls of galaxies spanning comparable distances. All of it was consistent with Lambda CDM's hierarchical structure formation, operating on the density fluctuations seeded by inflation. But Lambda CDM makes a specific prediction about the scale above which the cosmic web ceases to show coherent structure. The cosmological principle, the foundational assumption that the universe is homogeneous and isotropic on sufficiently large scales, sets a maximum scale for coherent structure. The theoretical calculation gives approximately 300 megaparsecs, or roughly 1 billion light-years, as the scale above which the universe should appear uniform. Structures larger than 1 billion light-years should not be coherent physical objects. They should be statistical flukes in an underlying uniform distribution, transient alignments that dissolve when examined at slightly different scales or orientations. The observations are finding structures much larger than 1 billion light-years. And they are not resolving into statistical noise when examined carefully. They are holding up. The giant arc, announced in 2021 by Alexia Lopez of the University of Central Lancashire, is a crescent-shaped concentration of galaxies, galaxy clusters, and gas clouds spanning approximately 3.3 billion light-years, observed at redshift Z approximately 0.8, corresponding to a time when the universe was roughly 6 billion years old. The statistical probability of such a structure arising by chance in a standard Lambda CDM universe was estimated at approximately 1 in 50,000 to 1 in 100,000. That is not zero, but it is the kind of probability that when it appears in observational data prompts serious scientific attention. The Big Ring, announced by the same team in 2024, is a near-perfect circular arrangement of galaxies and galaxy clusters spanning approximately 1.3 billion light-years in diameter at nearly the same redshift as the giant arc. The visual circularity of the structure is striking. Circles in galaxy distributions can in principle arise from baryon acoustic oscillation rings, the imprinted signature of the acoustic oscillations we discussed in the context of dark energy measurements. But the Big Ring's size does not match the baryon acoustic oscillation scale, which is approximately 490 million light-years in co-moving units. The Big Ring is nearly 3 times larger. If it is a real physical structure, it is not explained by baryon acoustic oscillations or by any other mechanism in the standard model. The most extreme case is the Hercules Corona Borealis Great Wall, a filamentary concentration of gamma-ray burst sources spanning, depending on the analysis method, approximately 2 to 10 billion light-years. If the upper end of that estimate reflects a real physical structure, it would constitute approximately 10% of the diameter of the observable universe in a single coherent object. That is so large that if real as a coherent structure, it would not just challenge the cosmological principle, it would shatter it. The academic response to these structures has been careful and methodologically rigorous. For each candidate megastructure, the critical question is whether it represents a physical overdensity, a real concentration of matter bound together or correlated by some physical process, or a projection effect and statistical fluctuation in the mapping of galaxy and quasar positions across a vast volume. Projection effects are real concerns in large-scale structure analysis. Structures that appear connected in two-dimensional sky maps may be separated along the line of sight and only appear associated due to the way the survey samples the galaxy distribution. The teams that have identified these structures are aware of this concern and have analyzed it carefully. The giant arc and the Big Ring are at similar redshifts and in adjacent regions of the sky, which reduces the probability that they are projection effects. A genuine overdensity in three-dimensional space at z approximately 0.8 across that region of the sky appears to be real. The statistical analyses, while not conclusive, suggest that these structures are more probably physical than coincidental. What do they mean cosmologically? If the cosmological principle fails at scales above a few hundred megaparsecs, if the universe retains coherent structure at gigaparsec scales, then the foundational assumption on which lambda CDM and all standard cosmological models are built is incorrect. The application of Einstein's field equations to the universe as a whole, which assumes homogeneity and isotropy, would need to be reconsidered. The Friedmann equations that describe the expansion history of the universe, from which the Hubble constant and the dark energy density and the age of the universe are derived, assume that the universe is uniform at large scales. If it is not, those equations are not the right description of the universe, and the parameters derived from them may be systematically incorrect. This is a very large if. The evidence for the large structures is suggestive, but not yet conclusive. The 4 statistical arguments are contested. The cosmological principle has been tested against many other observations and has held up remarkably well. Abandoning it would require not just a few anomalous structures, but a systematic statistical demonstration that galaxy correlations persist above the expected homogeneity scale across multiple surveys and multiple regions of the sky. But here is where JWST enters the conversation in a specific and important way. Webb's deep field surveys are beginning to provide high redshift galaxy catalogs with an angular resolution, a depth, and a spectroscopic completeness that no previous instrument could achieve. The JADES survey, the SEERS survey, the PRIMER survey, these are building catalogs of galaxies at redshifts from Z equals 4 to Z equals 15, with positions and redshifts precise enough to map the three-dimensional distribution of matter in the early universe at scales and resolutions relevant to the large-scale structure question. Early analyses of the JWST deep field data have noted that the distribution of high redshift galaxies shows more clustering, more spatial correlation than the standard model predicts at those redshifts. The early universe appears more clustered than it should be. This is the same pattern, expressed in the statistical language of galaxy clustering, rather than the visual language of individual megastructures, that the giant arc and the big ring express in their own way. The early universe is more structured than the model says it should be. The structures are larger than the model says they should be. The pattern is consistent across different probes, different scales, and different redshifts. A universe that is systematically more structured than lambda CDM predicts, at early times and at late times, in individual galaxy masses and in the large-scale distribution of those galaxies, is a universe whose initial conditions were different from what standard inflation predicts, or whose structure formation has been operating more efficiently than the standard model allows, or both. Either the density fluctuations seeded by inflation had more power on certain scales than the standard inflationary spectrum provides, or the dark matter properties that govern the gravitational collapse of those fluctuations differ from the cold, collisionless particles assumed in the standard model, or the physics of gas and galaxy formation in the dense early universe differs from the prescriptions built into the current generation of cosmological simulations. Any one of these would be a significant revision. All three acting together would be a transformation, and JWST, by providing the data needed to distinguish between these possibilities, is not just revealing the problem. It is methodically and with extraordinary precision pointing toward the solution. The data is constraining which modifications are consistent with observations and which are not. Every new JWST spectrum, every new photometric redshift, every new measurement of galaxy clustering, or morphology or chemical composition is adding another constraint to the space of viable models. The space is shrinking. The models that survive are becoming more specific, and the physics they require is becoming clearer. The cosmic web is not breaking, but it is bending in ways that the standard model did not anticipate. And Webb is the instrument watching the bending, measuring its magnitude, and accumulating the evidence that will ultimately tell us whether it requires repair or replacement. There is a theoretical concept that the large-scale structure anomalies are beginning to invoke in the cosmological literature, and it is worth naming directly because it represents the most radical possible interpretation of what the data might be saying. That concept is the failure of the cosmological principle itself, not as a useful approximation that breaks down at some scale, but as a foundational assumption that the universe straightforwardly violates at the scales that Webb and other surveys are now probing. The cosmological principle that the universe is homogeneous and isotropic on large scales is so deeply embedded in the mathematical framework of modern cosmology that it is easy to forget. It is an assumption rather than an observationally established fact. It was first introduced as a philosophical principle by Einstein in his 1917 paper on cosmology. Without assuming homogeneity, the equations of general relativity applied to the universe as a whole become enormously more complex. And in 1917, there was no observational basis for choosing any particular inhomogeneous model over any other. The homogeneity assumption was, at that point, a mathematical convenience justified by ignorance rather than by evidence. As the decades passed and the large-scale surveys accumulated data, the cosmological principle was increasingly treated as confirmed. The distribution of galaxies on scales above a few hundred megaparsecs appeared smooth to within the precision of the surveys available. But those surveys were always limited by the technology of their time. Limited depth, limited sky coverage, limited spectroscopic completeness. The structures now being identified, the giant arc, the big ring, the clustering excess in JWST's high redshift samples, are at the edge of what previous surveys could probe, and in some cases beyond it. If the cosmological principle fails at the scales being probed by current and future surveys, the implications extend far beyond requiring a new galaxy formation model or a modified dark matter prescription. They extend to the foundations of cosmology, to the way Einstein's equations are applied to the universe, to the way the parameters of the universe are extracted from CMB observations, to the way the age and expansion history of the universe are calculated. A cosmology built without the homogeneity assumption is not just a quantitatively different cosmology. It is a qualitatively different framework. It would require starting over with new mathematical tools from a new set of foundational principles. Most cosmologists do not believe this is where the data is pointing. The evidence for the large structures, while intriguing, is not yet conclusive. The cosmological principle has survived many previous tests. The simpler modifications, adjusted dark matter properties, enhanced small-scale primordial power, modified star formation physics, may well prove sufficient to account for the anomalies without requiring so fundamental a revision. But the fact that the most radical interpretation is even being discussed, that papers in peer-reviewed journals are examining whether the cosmological principle needs to be abandoned, is itself a measure of how seriously the community is taking the accumulating evidence of anomaly. JWST is not alone in pointing this direction. It is the most sensitive instrument yet in a sequence of observations that have been questioning large-scale homogeneity with increasing persistence. Its contribution is to push the evidence further, more precisely, and to earlier cosmic epochs than any previous survey. And each increment of precision has, so far, not resolved the anomalies. It has sharpened them. Chapter 9: What all of this means for life in the universe. We have spent most of this video in the Register of Physics and Cosmology talking about redshifts and mass functions, and the Hubble constant and the cosmological principle. All of that is essential. But there is a dimension of what JWST is finding that operates in a different register, a register that is, in some ways, more directly personal. It concerns life. Not life on Earth specifically, though that connection is implicit. Life in the universe. The question of whether life exists elsewhere, how common it might be, under what conditions it arises, and what conditions it requires. These are questions that the JWST data is beginning to address with a directness that no previous telescope could provide. And the answers are more complicated and in some ways more disturbing than the simple optimism that often surrounds discussions of extraterrestrial life. Let us start with the chemical foundation. Life as we know it, and as best we can theorize it might exist elsewhere, requires heavy elements. Carbon, nitrogen, oxygen, phosphorus, sulfur. The backbone chemistry of biology is carbon chemistry. The energy transfer chemistry is phosphate chemistry. The structural chemistry is dominated by silicon, calcium, iron, and a dozen other elements that exist on the periodic table precisely because generations of stars lived and died, forging them in nuclear reactions and distributing them through supernova. Life requires a universe that has been chemically enriched, a universe that has been through enough stellar generations to build up a meaningful abundance of heavy elements in the interstellar medium and in the planets that form from it. The Standard Model predicted that this chemical enrichment would take time. Billions of years of stellar evolution distributed across cosmic history, with each generation of stars building on the chemical output of the previous ones. The implication for the habitability of the early universe was clear. The very early universe, still dominated by pristine hydrogen and helium gas, was not a place where life could plausibly arise. Life required a chemically mature environment. JWST is revising this timeline. The detection of oxygen, and in some cases carbon and neon, in galaxies at redshifts as high as Z equals 14.32, corresponding to 290 million years after the Big Bang, means that chemical enrichment was proceeding faster and to greater depths than the Standard Model predicted. The early universe was not pristine for as long as the models assumed. Heavy elements were being produced and distributed into the interstellar medium earlier and more efficiently than the hierarchical structure formation models implied. This does not mean life was possible at Z equals 14. The oxygen abundances detected in these very early galaxies are still far below what we associate with chemically mature star-forming environments. The heavy element content of the gas is orders of magnitude lower than in our solar neighborhood. But the trend matters. If chemical enrichment proceeded faster in the early universe than models predicted, then the epoch at which the universe reached a chemical maturity sufficient to support the formation of habitable planets was earlier than we thought. How much earlier? The quantitative answer depends on what level of heavy element enrichment is required for planet formation to produce rocky, potentially habitable worlds. A question that planetary science and astrochemistry are actively investigating. But even a shift of a few 100 million years in the onset of chemical maturity is significant in the context of the history of life in the universe. It means that if life can arise wherever conditions are right, The first moment at which those conditions existed anywhere in the universe occurred earlier than our pre-JWST models suggested. There is a related finding from JWST that is even more directly relevant to the question of life, and it concerns the atmospheres of exoplanets. While JWST's cosmological discoveries have dominated the headlines, the telescope has simultaneously been conducting one of the most transformative programs in the history of planetary science: the atmospheric characterization of exoplanets. This is work that uses transit spectroscopy, observing the change in the spectrum of a star's light as a planet passes in front of it, with the atmosphere of the planet imprinting its chemical signature on the transmitted starlight. Hubble could do this for the largest, hottest planets. Webb can do it for planets far smaller and more Earth-like. In 2023, JWST published the first definitive detection of carbon dioxide in the atmosphere of an exoplanet, the hot gas giant WASP-39b. The spectrum was so detailed, so rich with spectral features from multiple molecules, that the scientific community immediately began referring to it as a new era in atmospheric characterization. But the more scientifically important observations have been of a different class of planets. TRAPPIST-1 is a small, cool red dwarf star, approximately 39 light-years from Earth. It is orbited by 7 confirmed rocky planets, at least 3 of which sit within its habitable zone, the range of orbital distances where liquid water could exist on a planet's surface, given the right atmospheric conditions. The TRAPPIST-1 system is, by every estimate of astrobiological relevance, one of the most important targets in the search for life beyond Earth. The planets are close enough to be studied in detail with Webb's transit spectroscopy capability, and studying them is exactly what Webb has been doing. The results have been sobering in specific ways. TRAPPIST-1b, the innermost of the 7 planets, was the first to be characterized in detail by Webb. The observations measured the thermal emission from the day side of the planet, the amount of infrared radiation the planet re-radiates to space, and compared it to what would be expected if the planet had a substantial atmosphere, redistributing heat from the day side to the night side. The result? The day side of TRAPPIST-1b is hot, much hotter than it would be if a thick atmosphere were present and redistributing heat. The inference is that TRAPPIST-1b likely has little or no substantial atmosphere. TRAPPIST-1c, the second planet, received similar treatment. Again, the thermal emission was measured. Again, the day side was hotter than expected for a planet with a thick, Venus-like carbon dioxide atmosphere. The inference for TRAPPIST-1c is similar. If an atmosphere exists at all, it is thin. These are preliminary results. They are based on a limited number of observations and carry real uncertainties. The absence of a thick atmosphere on TRAPPIST-1b and TRAPPIST-1c does not rule out thinner atmospheres, and it does not speak directly to the 3 potentially habitable planets further from the star: TRAPPIST-1, E, F, and G, which are the most astrobiologically interesting members of the system. More observations are scheduled. The story is not complete, but the early TRAPPIST-1 results have introduced a note of scientific caution into the optimistic narrative about red dwarf habitability that has been a staple of exoplanet science for the past decade. Red dwarf stars are the most common type of star in the galaxy, and their planetary systems are the most accessible to current atmospheric characterization techniques, precisely because the planets orbit close to the star, producing frequent transits detectable with Webb. If the planets of red dwarfs generally lack substantial atmospheres, because the intense stellar activity of red dwarfs, which emit regular and powerful flares of ultraviolet and X-ray radiation, strips atmospheres from close orbiting planets before they can stabilize. Then the population of potentially habitable worlds in the galaxy is smaller than optimistic estimates suggested. This is not a definitive conclusion. TRAPPIST-1b and 1c are the closest planets to their star, the most exposed to atmospheric erosion. The habitable zone planets farther out may have retained their atmospheres or had them replenished by volcanic outgassing. The Webb results on the inner planets are a warning, not a verdict. But they are a warning that the simple version of the story, red dwarfs are abundant, their planets are accessible, life is probably everywhere, may need revision. And there is a deeper, more philosophical dimension to what the JWST cosmological findings mean for the question of life in the universe, one that connects directly to the disturbing findings about the early universe and the Standard Model's failures. The universe that JWST is showing us, the universe with impossibly early massive galaxies, with ancient spirals, with overgrown black holes, with a split expansion rate, with large-scale structures that exceed the cosmological principle's predictions, is a universe that is more complex, more structured, more active, and more chemically evolved at early times than the Standard Model predicted. And chemical complexity, structural organization, and long time scales for development are among the properties most relevant to the emergence of life. If the early universe was more chemically enriched than expected, and if planets capable of supporting life could form earlier than the Standard Model implied, then the history of life in the universe may be longer and more distributed across cosmic time than we previously thought. The universe may have had pockets of chemical maturity, regions of it capable of supporting the formation of habitable rocky planets, earlier in its history than the Standard Model's timeline suggested. This is speculative. We do not know the minimum chemical maturity required for life. We do not know whether life's origin requires specific conditions that are rare regardless of chemical availability. We do not understand life's origin well enough on Earth to extrapolate confidently to other environments. But the direction of JWST's findings, the universe is more mature sooner than the model says, is a direction that, if anything, expands the window of cosmic time during which life might have arisen somewhere. At the same time, the other dimension of JWST's findings, the Hubble tension, the possible dynamical dark energy, the large-scale structure anomalies, raises a more uncomfortable possibility. If the universe's expansion history is different from what lambda CDM predicts, if the dark energy component is evolving rather than constant, then the universe's long-term future may also be different from standard predictions. A universe with dynamical dark energy could expand more or less rapidly than the cosmological constant model predicts. In an extreme version, the Big Rip scenario, dark energy could grow strong enough to overcome not just gravity at the largest scales, but the binding forces within galaxies, then within stellar systems, then within individual atoms, tearing the universe apart in a final, catastrophic expansion. The Big Rip is not predicted by the cosmological constant model, but is permitted by certain dynamical dark energy models. This is the most unsettling aspect of the dark energy uncertainty. It is not just an academic question about the history of cosmic expansion. It is a question about the ultimate fate of the universe, and implicitly, about the ultimate fate of everything in it, including any life that has arisen or will arise. A universe whose dark energy is dynamical and evolving in a particular direction could have a finite future, not billions of years, but potentially much less in extreme scenarios. The constraints on the dark energy equation of state from DESY and from Webb are pushing towards scenarios with dynamical dark energy. And while the Big Rip is not the most likely scenario in current data analyses, it is not as firmly ruled out as it would be if dark energy were definitively constant. JWST is the instrument that is most directly probing both ends of this question. The early universe, where life's chemical foundations were established, and the expansion history, where life's cosmic future is written. Its findings at both ends of the cosmic story are more surprising, more complex, and more demanding of new physics than the pre-launch scientific community expected. And the intersection of those findings with the question of life, with the question of what kind of universe we live in, and what it means for the existence and persistence of complex questioning beings within it, is not merely scientifically interesting. It is the question that motivates the whole enterprise. There is a specific, uncomfortable implication of the JWST life-related findings that rarely makes it into the public discussion, and it deserves to be stated plainly. It concerns what the TRAPPIST-1 atmospheric results, combined with the broader picture of stellar flare activity in red dwarf systems, suggests about where in the galaxy life is most likely to arise. Red dwarf stars, spectral type M stars, cooler and smaller and dimmer than our Sun, constitute approximately 70% of all stars in the Milky Way. If their habitable zone planets generally retain their atmospheres and support life, then the galaxy is overwhelmingly dominated by planets around red dwarfs, and the probability of life in the universe is extremely high. If those planets generally lose their atmospheres to stellar flares and UV radiation before or key life can take hold, then the relevant stellar hosts for life become the rarer Sun-like stars, spectral types F, G, and K, which constitute only about 15% of the galaxy's stellar population. The statistical implications are enormous. A factor of 5 reduction in the fraction of stars that can host life translates directly into a factor of 5 reduction in the expected number of life-bearing worlds. Webb's TRAPPIST-1 results are preliminary. The habitable zone planets have not yet been characterized. The story is not complete, but the early indications are not encouraging for the most optimistic scenarios. And the implication that life's cosmic address may be more specific and more restricted than the simple abundance of red dwarfs suggested is one of the more quietly consequential things the most expensive telescope in history has begun to suggest in its early years of operation. We built Webb, ultimately, to understand where we are, not just spatially, cosmologically, to understand the universe that we are embedded in, that produced us, that will determine how long the conditions for our existence continue to be met. What Webb is telling us about that universe is not reassuring in the simple way that confirmations of the standard model would have been reassuring. It is disturbing in the specific sense that the universe is more complex, more surprising, and less completely understood than we thought. But disturbing is not the same as threatening. The universe that Webb is revealing is a stranger and more wonderful place than the one we thought we understood. Its anomalies are not catastrophes for science. They are invitations. Conclusion. Let us return to something that was said at the beginning. The James Webb Space Telescope was not supposed to break physics. Having spent this video cataloging everything it has found that challenges, disturbs, and refuses to fit the standard model, it is worth asking, has it broken physics? No, and the reason it has not is worth stating clearly, because the distinction between this challenges the standard model and physics is broken is one that popular science communication sometimes blurs in ways that mislead more than they illuminate. Physics is not broken. The laws of physics, the specific, mathematical, experimentally verified regularities that describe how matter and energy behave, are not in question. General relativity works. Quantum field theory works. Nuclear physics works. The Big Bang happened. The universe is expanding. Dark matter exists in some form, and dark energy exists in some form, and the large-scale structure of the universe is a cosmic web produced by hierarchical gravitational collapse. None of that is challenged by what Webb has found. What is challenged is the standard model of cosmology, lambda CDM, as a complete and final description of the universe. And that is a different thing? Lambda CDM is not the laws of physics. It is a model, a set of physical ingredients and initial conditions that, when the laws of physics are applied to them, produces a simulated universe that matches observations. The model is extremely good, extraordinarily good, in many respects. But it is not finished, and JWST is showing us where it is unfinished with a precision and a scope that no previous telescope could provide. The unfinished places are real, and they are significant. The impossibly early massive galaxies, the ancient spirals that formed before the dynamical timescale permitted them, the overgrown black holes that required more time than the universe had given them, the split expansion rate that gives different answers depending on when you look, the hints of dynamical dark energy, the large-scale structures that exceed the homogeneity predictions, the early universe's compressed timeline of chemical enrichment and cosmic dawn. Each of these anomalies is real data. None of them is explained. All of them are pointing in the same direction, toward a universe that is more complex, more rapidly organized, more energetically efficient in its early assembly than the current model accommodates. What happens now? What happens now is science doing what science does at its best, taking the anomalies seriously, building models that try to account for them, testing those models against the growing body of Webb data, and iteratively converging on a better description. It has happened before. When the perihelion of Mercury refused to precess the way Newtonian mechanics predicted, it was an anomaly that pointed toward general relativity. When the orbits of galaxies refused to flatten at the edges the way visible matter permitted, it was an anomaly that pointed toward dark matter. When the supernovae of the late 1990s refused to dim at the rate an expanding universe, without a cosmological constant, would predict, it was an anomaly that pointed toward dark energy. Each of those anomalies was, in its time, disturbing. Each was labeled by some as evidence that physics was broken. Each turned out to be evidence that physics was incomplete. And each resolution of the anomaly expanded human understanding of the universe in ways that were worth far more than the comfort of confirming what was already known. It is also worth remembering how long those transitions took. The perihelion of Mercury was an anomaly for more than 40 years before general relativity resolved it. The galaxy rotation curves that pointed toward dark matter were observed in the 1970s. Dark matter remains undetected and theoretically poorly constrained 5 decades later. The accelerating expansion of the universe was confirmed in 1998. We still do not know what dark energy is. The history of physics is not a history of rapid resolution. It is a history of anomalies sitting in the literature for years, sometimes decades, patiently demanding better theories from a field that is working as fast as it honestly can. Webb's anomalies are in that tradition. They are probably not going to be resolved next year. Some of them may not be resolved in this decade. The Hubble tension, which has now persisted for nearly 6 years at 5 sigma, is showing no signs of easy resolution. The impossible early galaxies are accumulating at every new survey depth, each new spectroscopic confirmation adding another data point that the standard model must account for. The large-scale structure anomalies are growing more precise as the galaxy catalogs improve. The dark energy hints from DESI are waiting for confirmation with a larger sample. What this means in practice is that we are living through the accumulation phase, the phase in which data mounts, anomalies harden, the inadequacy of the existing model becomes progressively clearer, and the theoretical community searches for the new ingredient that will resolve everything at once. It is not a comfortable phase. It is characterized by uncertainty, by proliferation of competing theoretical proposals, each of which resolves some tensions while creating others, by a healthy skepticism about every apparently decisive result until it is confirmed independently by multiple methods. But it is also the most exciting phase of science, the phase where the next great discovery is closest, the phase where the data is already in hand and the theory that will explain it is being built somewhere right now by someone who is staring at the numbers and beginning to see the shape of the answer. Webb's anomalies are in that tradition. Not every anomaly produces a revolution. Some are resolved by improved measurements that reveal hidden systematic errors. Some are resolved by modifications to existing models rather than replacements of them. The field will determine which category each of Webb's findings falls into, with methodical precision and appropriate scientific humility as more data arrives. But some of them, the Hubble tension, especially with its 5 sigma persistence across every attempted resolution, and the impossible early galaxies at the highest confirmed redshifts, with their oxygen emission and their stellar masses. These have the quality of things that will require new physics, not adjusted parameters. New ingredients, something the model does not contain, that the universe was telling us about all along, but that we did not have an instrument sensitive enough to hear. We have that instrument now, and it is telling us something that the universe has been trying to say since the first stars lit up in the cosmic dawn. Something that the light from billions of galaxies at billions of years' distance, has been carrying across the void toward us. Something that, now that we can finally receive it, is changing our understanding not just of what the universe contains, or how old it is, or how large it is, but of what kind of universe it is. Stranger than we thought, more complex than our best model captured, more efficient in its first moments, more structured on its largest scales, more surprising in its expansion history, more uncertain in its future than the 30 years of Lambda CDM success had led us to expect. A different universe, not a broken one, a richer one, a deeper one that is in the specific and important sense of having more to teach us than we imagined, better than the one we thought we understood. That is the gift of a telescope that was not supposed to break physics and instead found something that demanded better physics. That is what science looks like at the frontier. And the frontier, it turns out, is everywhere Webb looks.